Today here with me is Charles Isbell. Charles is a professor at the Georgia Institute of Technology's College of Computing and is the John P. Imlay Jr. Dean of the college, where he specializes in machine learning and human-centric AI. Most recently, Charles gave the opening keynote of NeurIPS, the top machine learning conference, and he was elected into the National Academy of Arts and Sciences, an honor that goes to only a handful of computer scientists each year. So good to have you here. Welcome, Charles.
Thank you. I am very happy to be here too. Looking forward to our conversation.
So, Charles, I'm so excited to get to chat with you. Normally we meet, many times a year, but now with the pandemic, it's been a little while. But the last time I saw you was when you gave the NeurIPS opening keynote, kicking off the conference together with Michael Littman, of course, at the time. And this is this is pretty much the biggest venue there is in machine learning. And you're giving this opening keynote. And a lot of people, I would say, focus on their own recent research and tell a story about the latest, greatest work they've done, the latest papers, but you decided to structure it quite differently. Can you say a bit about that? What was your thought process and how you went about setting up this keynote?
So it was an interesting thing. So as you are well aware, as is everyone else, we were in the middle of a pandemic. I got asked if I would do the keynote. And like with most things, when someone asked me a question, it went into the bit bucket of my email, so I didn't see it for a couple of days. And the follow-up was, well, we want you to give you the opening keynote. Do you think you could do it? Something in the space you've done? And I thought about it and I said, yes, of course, I'd be honored. It had been a while since I've actually physically been at NeurIPS, and of course, my students there all the time. And it is the first conference I ever went to, so it's one that holds a special place in my heart. And I thought, if I'm going to do this and it's going to all be recorded and I can do what I want to do something special. I feel like I'm at the point in my career where I don't have to give a talk about just the things that I'm doing, that I should be thinking about my students and sort of broader work, and more importantly, big kind of vision of what's happening and what's sort of going on in the field. And certainly for an opening keynote, because this is supposed to set off a kind of tone. And I thought, well, if I'm going to do that, I'm going to pre-record it and I'm going to be able to, I should try to do something interesting. So if I'm going to do something interesting, how do I do something interesting? And of course, I thought I should talk to Michael Littman, because anytime I do anything around video that is interesting, Michael seems to be involved, and we work really well together. And we've got 2 classes that we've done together for our the online master's program. And Michael and I sort of went through it and talked a little bit. And I said, I really want to talk about this sort of space of ethical machine learning, but less about that, more about responsible machine learning. What does it mean that we've got these incredibly powerful tools and these major impact on the world, and it seems to be growing so fast? And it came out of this kind of realization, not just that machine learning is machine learning and interesting. Of course, it's machine learning and it's interesting. I have to believe that, but that it's having this outsized impact on the world, and we are not responding to it. One of the things that I think has been true for computing generally and machine learning in particular over the last, 5 or 6 years, is that we're growing exponentially. And I mean that in the technical sense of the word, right? We're growing exponentially, and our problems are growing exponentially, but our solutions are linear, right? And, exponential beats linear in the long run, no matter what you do. So the only thing that you can do to do something kind of to deal with it is to try to hit a discontinuity, right? You have to try to do something different. And I thought, well, this is my opportunity. I want to talk about the big hole in what I think machine learning has been doing for a while, which is not considering the entire scope of the problems that we're being asked to solve. We're focusing on something very narrow because that's easier for us, because it's sort of probably why we got into it in the first place. But we can't pretend there aren't things that come before the data shows up on our desk, and we can't pretend there isn't stuff that comes after the models that we produce. And then I thought, well, if I'm going to do that, then I'm not the biggest expert on that, even though I've done some work in the space and I care about it. But I should be bringing in other people. If this is a large conversation, it's a conversation that involves other people. I could never do that in person, so let's do it. And so the only we interviewed 14 different people over about 5 months. Each of those interviews, by the way, is like 40 minutes long, and we figure out how we're going to edit it down to 45 minutes. And what we were missing was the kind of through line in the sort of hook. So like we got to have something that makes it interesting and brings people along in sort of the story. And I don't know I think it was Michael who had the thought about doing A Christmas Carol. And then once that was all together, that was just it. And it was just turning the crank and saying the right things and, just talking like we would be talking anyway. And that's how we put it all together. It helps, by the way, that, I'm the dean. So I actually have a communications department and people who know how to actually put things together and producers and all of that. We could put something together, and we did it. And it was a lot of work behind the scenes, but I think it was worth, at least for me, it was worth it. I learned a lot, and I hope it kind of set up a conversation or two that I think the field desperately needs to have.
I really enjoyed it. And what really struck me, especially, is the way you set it up in the beginning, the hook, where of course, Michael was playing the naive machine learning researcher, I guess, and you were the more mature machine learning researcher understanding what's actually going on. But Michael coming in and saying, "Hey, life is good. My papers are more popular than ever." And you kind of come in and say, "Well, do you even know what the consequences are of all the papers that you're writing?" Which, of course, ties into actually things you've been thinking about for a while, which is thinking of machine learning not in isolation, but more as a systems-oriented effort. Which very few people do, because usually it's nice to just write a paper. You work on something, write a paper, and it feels isolated, even if it might not be. And so I'm curious where your latest thinking is on how to go beyond just per paper thinking to kind of broader systems view on things.
So two things. First off, let me just say I like nothing more than the idea that Michael is the naive machine learning guy and I'm the mature one. I will be quoting you on that, and I will hold that over Michael for the rest of his life. So I love that. But I think you're saying this exactly right about this kind of illusion and sort of story we tell ourselves that our work is isolated, and that we can think about it that way. And I think before asking a question like, well, what would it mean to do more systems thinking? You have to ask yourself, why are we in that place? And there are a couple of reasons. Some I think are it's easier. It's sort of what people want to do anyway. I mean, a lot of us kind of suffer from the engineer's disease, right? Which is you put a problem in front of us and we just solve the problem without thinking about whether it's the problem that needs to be solved or it should be some other problem. It's very easy to do. And I know I fall into this trap all the time, right? Oh, look, there's a problem. It's shiny and it's interesting. And oh man, what if you divide by 2? And you just really, really kind of dive into it. And that's fun, right? I mean, you don't get this far into what it is we all do, particularly on the academic side, unless you really enjoy solving those kinds of problems. They're almost like puzzles, right? But I think there's something else, and I think this is really what gets to the heart of your question, which is what are the incentives? How are things set up that get us here? And I think that almost everything about sort of the research world, and in particularly true for computing and machine learning, is shoves you towards these, I won't say least publishable units. I think that's further than I want to go, but to these kind of well-articulated nuggets of things that you're doing that you can point to where you've made some delta in the field, because you have to earn tenure, right? You have to get credit for them. What else do we have but credit in the field anyway? And you have to be able to point to these things and then build this kind of story around them. And that's how you're evaluated by all of your peers. It's how you're evaluated by those who are going to determine promotion, who's going to determine whether you're in an academy or not, or whether you're going to get some award. It's just everything about the incentives are set up to drive us towards that. And I think it's much of what we would do anyway. I mean, I don't want to psychoanalyze billions of people, but I do think it's a kind of, it's a reasonable place to start. So then to answer your question, I think there are kind of two ways you have to touch both of those things, the kind of intrinsic, what drives us as researchers, and the larger incentive structure. And I think the larger incentive structure is you have to reward people for thinking beyond the small thing that you're doing, right? Giving giving credit and positive feedback and outcomes for the sort of systems thinking. You have to either require it, which feels kind of more like a stick, or you have to provide the best paper awards go to the system thinkers. The accolades go to those who build a story across time and really think hard about the impact of what they do. But on the intrinsic side, I think it's really about defining the problem in such a way that it becomes interesting to solve that problem. It's not to, if I can quote Michael Kearns, this sort of relentless pursuit of accuracy as the way that you know that you're doing well. That's not really what you should be caring about. You should be thinking about the long-term impacts of what it is that you're building, and you should be measuring your success on that. Yes, the system has to do that, but you have to decide that it's an interesting research problem, and that's what it means to have good taste. You have to tackle both of those things at once, and that is, of course, in part the job of educators. Universities have to do that. People like you and me, the people who do, who have students and who evaluate new faculty and people who would define what's going on. You have to say that this is important and evaluate people accordingly, and then define their problems as such. And that's what I'm sort of dedicating at least the dean half of myself, as well as the professor half of myself, to doing over the next several years.
Now, that's not easy, right? Because that's not what we're used to doing. So how do you even get started on that?
Well, I agree, it's not. And I will tell you that it's not a technical change, it's a cultural change, right? And I feel very strongly that cultural change almost always starts from the top, because the people at the top are the ones who set the incentives. They're the ones who model what it is for others to do good work. And so, I mean, it's not fair to change the rules on people halfway through and all these other things, but it's going to come from above at least as much as it comes from below. I mean, we already are getting pressure from below, right? Because there are new people being brought into the field, people from very different backgrounds, people had very different experiences. They're saying, we believe that these things are important. These are things that we happen to care about. It is bubbling up from below. But the cultural shift we're talking about has to be driven from above as well. So then the question is, who's above? And I think the people who are above are, senior researchers, the people who are sitting in academies, who are running conferences, who are, deciding what good work is, and they have to be willing to put their reputations out there and then define technically what that means. What does it mean to do good work in the field? Technically, yes, but also what do we expect culturally as a community for having done good work? And we'll do it in fits and starts, and some of the ideas will be crazy in retrospect, but that's okay. It's an ongoing experience. I mean, so to wrap this up, I think I would say, you should treat it the way you would have treated. You would have thought about the world if this were, the 1960s, and you were trying to think about AI. What does it mean to do AI? What does it mean to do computing and computer science? That was a new. That's just electrical engineering or math, depending upon where you were coming from, and yet somehow from there to now, we're living in a world where what it means to do good work in those kinds of fields, including the ones where we sprang from, are very different. Right.
Right. Now, I'm curious, as you start thinking about this, were there any specific events or scenarios that you just were faced with that made you say, oh, wow, I really need to start paying attention to the impact aspect of the work we do, rather than just push the frontier of what we're capable of?
Yeah, so there was lots of little things kind of happening together. A lot of it sort of my personal journey, kind of going through research, came from stuff that I did very early on, actually before I became a professor, around modeling human behavior and building systems like Cobot, if I can really go back a long time ago, of building agents that actually had to interact with humans in social situations. And you very quickly realize that all of the metrics and techniques that you use to determine that you're doing well just don't apply. It turns out people don't behave this way. Once you recognize that the world is not going to give you, a scalar reinforcement signal of the sort that you want, the way that we pretend the world is kind of constructed for our MDPs and such, you kind of have to start thinking more broadly. And once you move from that kind of sort of machine learning and social situations to modeling humans and trying to influence them, and you start to realize, oh, wow, I can do. So in particular, I did a lot of work with David Roberts, who was my student at the time, who's now being a professor in North Carolina, does a lot of different work now, but done a lot of really cool things. One of the things that we did is we spent a lot of time thinking about drama management, entertainment management. I went through a bunch of names, and it became pretty easy, it turns out, to sort of make people do what you want them to do. And when you think about it just as that problem, it's very cool. So you come up with all these really cool techniques and, oh no, it's a hyper exponential problem, but you can be very clever and make it a linear problem. And you just do all these cool things and you're really excited. And then somewhere around the eighth paper being published, you think about, we basically just codified clever ways of manipulating human beings. Maybe we should feel bad about that. And once you put all these kinds of things together, you realize you have to think much more carefully about the problems that you're doing. So once you engage as a research question with modeling, influencing, whatever, human beings themselves, and you see how they react, I think it's very difficult not to at least notice that you might be doing something that requires more thought than, minimizing sum of squared error or maximizing long-term expected reward. That was my own sort of thinking going on in the back of my head over the last several years. But then you started having people, not me certainly, but you had people out there in the world who were focused explicitly on the question of ethics, the question of, is this right? Are the consequences of this right? What are we not thinking about? And once you start listening to those voices and you tie it in with the kinds of experiences that I'm talking about, I just don't see how you can walk away from it. It's too obvious. And of course, I've had my own personal experiences with this. I've certainly been policed in a way that I know that you can justify from data, but which are not, let's just say, not the set of metrics you should be maximizing. And once you put all those kinds of things together, I just feel it's an imperative. It's just an imperative to do this. And I hope that most people come to this kind of conclusion. Ultimately, you don't have to do it just because of your own personal experiences, but you should have at least some empathy, if not sympathy, for how the things that you build are going to have impact on the world. I guess the way I would summarize it, if I had to, is you keep saying that you believe that what you're doing is important, and that's going to have an impact and can ultimately change the world. So if you believe that, then you have to engage with it, that what you're doing is important and is ultimately going to change the world. You can't have it both ways. You can't say we're the most important subfield, we're changing everything, the world is going to be different because of us, but I don't have to think about any of that. I can just pretend it's this little. You can't have both of those things. It's an inherent contradiction. So engage with it or don't, but admit that is the case.
When you say you see these examples of essentially AI becoming impactful in the world, yet having some negative consequences along the way, thanks to being so powerful in some sense, actually becoming powerful in a negative way. What are some examples of things that you saw and that really, made you think, there's no way I can ignore this. I need to start spending time on that. What is the impact in the real world?
The number of examples that are out there of just the deployment of computers, the deployment of data, the deployment of machine learning that has real impact on the world. I mean, there's a lot of those examples. Here's a few. So, and some of these have been sort of popularized, and of course, there's lots of details and nuance here. But I think in the main, it's very difficult to ignore them. You have to engage with the realities. We know that people use computing systems and data as black boxes to do things like to predict whether someone is likely to commit a crime. And therefore, this has an impact on whether you're going to be granted parole, how long your sentences are going to be. But we can't predict whether someone's going to commit a crime. In fact, even if you believed you could, the data we have is not about whether you're committing a crime. The data is about whether you're being arrested. And if you're being arrested, whether you are convicted. If you're convicted, how much time you serve, right? So we know we're not even getting the kind of data that we want, but we pretend we are because it feels like it's the same thing as will someone predict a crime? Will someone commit a crime? So once you do that, then you build a system that starts to predict that people are going to be more likely to commit crimes. And then you act on that, which of course is going to have this kind of positive feedback loop of, well, we're going to throw more police officers there. We're going to take people from certain communities and we're going to have them spend more time in jail. We're going to make them less likely to get parole and so on and so forth. Then you just get this kind of this sort of cycle of unfortunate consequences, and these things are unavoidable. And it's because we treated it as a simple problem, but really it's this much larger problem. And we pretended, because there wasn't all this stuff beforehand, that the data we have says something that it doesn't actually, the data don't actually say. But you just attack it that way. You treat it that way because it's a computer doing it. And it's, of course, objective by definition, as if the data and the systems and the processes that got you there are not themselves coming from a place other than disinterested objectivity. You can take an example like crime. You can take an example like what Amazon did, where they were predicting whether someone is going to succeed and they should be hired. Well, it turns out they aren't predicting whether you're going to be hired or not. What they're doing is they're modeling the biases and opinions of the hiring managers, right? So you learn that you should be hiring men and not women. That's not actually what you're learning. What you're learning is that they tended to hire men and not women, right? And there's lots of these kinds of examples. And it's very easy to fall into this kind of trap if you treat it as an isolated problem and don't worry about what came before or what's going to happen after. And there are real consequences that come from ignoring that. So, I think you can't, it helps a lot to think about the fact that data are not isolated things that come from some higher authority, but they represent processes that exist and that happen the way they happen to happen. They are not themselves sacrosanct. And so you have to ask questions about that and think very hard about it in order to know what question you're actually answering.
So Charles, what's really interesting to me, what you mentioned is, well, there is so many layers to this, because the first layer is there are existing processes that are not even the way we would want them to be, but they are there, run by humans. And these existing processes that are kind of not what we want them to be, generate data. Then the AI systems train on that data. And it's not just that, what you're saying is, it's not just that they then replicate the processes. In fact, by replicating them, they generate even more data. And by training on that more data, it effectively reinforces itself. Mm-hmm. And it becomes even more, very likely a more extreme version of the already broken process that we had before. Is that right?
Yes. And by the way, not only does it become a more extreme version of the process we already have, we validated what it is that we were currently doing. We've done it behind a bunch of equations or a bunch of black boxes we don't understand, but we attribute objectivity to it, which is also a very human thing to do. And it allows us to do worse and to do more. So there were kind of two things that really pushed me in this direction most recently. One was, and both of them come up in the NeurIPS talk that you referenced. The first was around cameras, and the other had to do with personal experiences that I had being pulled into a Twitter war, which I'd like to never do again, around generating images. So I guess they both have to do with images. So the photography one was really amazing to me. So I have a lot of friends who care about photography, and this is sort of well understood history. But when cameras were built, right, cameras, it's an engineering problem. And what's sort of fundamental about engineering is trade-offs, right? You can make something more expensive, you can make something less expensive, you can make something better in one part of the world and different, there are fundamental trade-offs. So early cameras, both because of the mechanics of capturing light, but also because of the chemistry of film, were optimized for what amounts to pale-skinned people with contrasted clothes. Just what it was. And there are reasons for this, and none of them have to be nefarious. They just are what they are. And so early cameras, it turned out, took very good pictures of people who look like you and very poor pictures of people who look like me. But this was built in to the way photography was done for decades and decades. And it meant that the images that we see, all of the foundational work that we did, including work that was inherited by computer vision, sort of started from this kind of premise of what it meant to have a real picture, what kind of pictures you took, where lighting went, what was, how contrast worked, everything about it was sort of built into it. Now, it happened so long ago that we forget that, but it has these consequences much further down the line. By the way, apparently it's the case that the cameras didn't get good at pictures of more chocolate-colored people until after furniture companies and candy companies decided that they needed to be able to take pictures of mahogany furniture and chocolate and these.
Oh, wow.
And then suddenly you were able, the trade-offs in the engineering problem came along and they changed. And so suddenly we got better kind of pictures. But that initial set of assumptions, the initial set of what it meant, metrics, in fact, of what it meant to take a good picture, drove things for decades, and again, was inherited by the way that computers process images. So you end up in these kind of, that's sort of weird, right? I mean, people sometimes get upset when I say that. They go, oh, well, you're taking it. This isn't an agenda, except insofar as it's about what physics actually is and where the data come from. But the data are driven by decisions that were made decades before you were born. They're driven by human beings who are trying to solve some other problem. And if you're unaware of it, then you will create issues later on, and that will be used well after you're gone or well after your algorithm is bought up by a company somewhere. And that's kind of crazy. So what we saw last year, where this all kind of came out, was in generating images from other images. You take an image of someone, you downsample it, so it's just pixels, and then you try to create a new image out of it, and you see what you get. And it worked very well. People were very excited about it, and it was awesome. And then someone noticed that if you take a picture of Barack Obama and you downsample it, and then you generate a new image, you somehow manage to turn him into a white guy. And then, in fact, this kept happening again and again. So there's a picture of me floating around out there that goes from what I look like to blonde hair, and it's very strange sort of look. Like you can see, like we seem vaguely related. And in fact, if you stare far enough away, skin tone is the same. And yet anybody who's certainly grown up in the United States would recognize that the original picture was a black man and the new picture was a white man, and do this again and again and again. And this led to a pretty heated set of exchanges on various parts of social media about, well, where was the problem coming from? Was it a data problem? Well, clearly, if you just, it was just because you trained on images that all happened to be in this space. And therefore, that was the issue. Of course, there's problems with that. One is, if it's true, then it's problematic that everyone's training on just, images of young white people between the ages of 22 and 50 or something like that. That in and of itself is a problem. But actually, it's worse than that. It turns out that isn't the problem. There were people who did some experiments to see, well, what if we trained on only people from sub-Saharan Africa? Turns out you actually don't get the results that are anywhere near as good, because there's something about the way the learning algorithms is set up, the hyperparameter, whatever it is, that made it so it just worked better with pale-skinned people with contrasting backgrounds than it did with brown-skinned people with less contrasting backgrounds. And so it wasn't just a question of the data. It matters where you set all the little parameters here and here, and all these little decisions that we never share in our papers, that we never worry about, have these huge impacts on the output that we have. And if it can happen for something as simple as taking pictures, that turns into generating images, which turns into matching images and determining whether somebody is someone you think you're looking for. And now imagine how it works with everything else we do, with health. Imagine how it can impact whether you get a loan for a home. Imagine all the ways in which these simple little decisions you're making can have an impact on the real lived experiences of the people who are going to ultimately be impacted by this technology. And if it can have that kind of impact on something as simple as picture taking, and all the rest of this, then don't we have an ethical responsibility to at least think about that problem and to come up with algorithms that are at least aware, or processes that are at least aware of what of the things that we can do. We have to at least ask the question and ask whether there's anything that we can do.
Now, what you brought up there, Charles, I mean, I think it's so interesting that essentially, as machine learning researchers, we're used to tuning a lot of hyperparameters behind the scenes, the architecture of the neural network, the learning rates, weight decays. I mean, all the kind of things that are just mathematical parameters behind the scenes that we just play with till we get a better result. Mm-hmm. And then I feel like what I'm hearing is what you're saying is that's what we're used to doing. But then when we open source or release our code, the people who are going to use it are actually not going to retune all of that, not redo everything that we did. We did it for a benchmark. That benchmark is not directly matched with the real world. So we release something that's really good for the benchmark, but is not necessarily really good for a real world application. And people just run with it. And then maybe the question is, how I mean, that seems a research problem in itself, right? How to release things in a way that a practitioner will, in some sense, get either at least the understanding of the limitations, but hopefully also the understanding of how to kind of repurpose it for their application in the right way.
Right. And by the way, I'll say there's at least two things. One is you said to get a better result, right? Which begs the question, right? Because you think you know what the better result is. The better result is probably something like accuracy. But maybe that isn't the right better result you should be getting. That's important, right? We're always asking ourselves, what does it mean to have a better result? How do I know I'm doing better or worse? But the other thing is, you say, we fiddle with these hyperparameters. We don't understand what these hyperparameters mean. Not really. We just are fiddling with them in order to get to I think most people anyway. So in that sense, we're all practitioners, right? Because the goal was, I have this new algorithm and I have this theory about how if you change something here, which only matters to those of us who spend our time worrying about this. But if we change this little thing over here, we'll be able to deal with a much bigger set of problems in the space I happen to personally care about. But, and so we fiddle with gamma till it's 0.7 or alpha when it's 0.01. And it doesn't matter. We don't really know what those things mean, only that it worked for us. So we're not even engaging with the question that we need to, the engineering part of what it is that we do in order to get the answer that we get. We just get the answer that we get. And then we, as you say, we release it out to the world, and we couldn't explain to the practitioner what we did. I can't remember who did this. It was someone in Peter Stone's group. I got a phone call asking me about the discount rate that I used for a bunch of work that I had done in the late 90s and maybe early 2000s. And I realized I really had no idea. I tried to look it up, and I think it was 0.7. And why I'm saying this? Why was it 0.7? Well, because that was the default value that came with whatever package it was that I was using or whatever code that I had inherited. And it worked. And because it worked, I didn't change anything. I had no idea why 0.7, or maybe if I had done 0.8, it would have worked better. If I had done 0.6, it would have been worse. Who knows? I have no idea. But it was just set up that way. I had no way of justifying to anyone or myself, other than it happened to work, for why that was the particular value that I had. And I think there's something really important in the way that you phrased the question. Right? It's that these hyperparameters matter. It matters that you set this to 0.7 instead of 0.8. Because if it doesn't matter, then why do we have them? Mm-hmm. So given that it matters, why don't we spend time actually explaining them to ourselves and explaining them to the people who are going to use our systems? Well, it's because we don't value that, and it doesn't matter for lots. It doesn't seem to matter to us for other reasons. Now, I should be clear about something I think is really important. One is, I am not upset with my colleagues, or myself for that matter, for not understanding why gamma equals 0.7 is better than 0.8, or pick whatever your favorite Greek letter is and whatever your favorite algorithm is. I'm not upset with anyone. I don't think that we're terrible people. But we haven't engaged in it. We haven't thought about it as this big, complicated problem because we've been focused on this part of it. And if we just broaden our view a little bit more, then we start to realize there's really interesting technical questions. There's really interesting research questions to understand about these big systems that we build and that we set free in the world. And then if you make it just a little bit bigger, you realize, the data matters as much as the algorithm. Well, then I need to know about the provenance of the data. And then I need to know where it came from. And what does it mean? And what does it represent? And it's very hard once you open it up just a little bit, it's very hard not to realize you have to open it up as wide as possible. And that is a justifiable and important part of what we should be doing as machine learning and AI researchers.
I couldn't agree more, Charles. And actually, I want to give a quick highlight here from a previous conversation where we're talking with Olga Rysukovsky, and we talked with Andrea Tomas, and both of them said that when they tried to use a speech recognition system for their robotic experiments during their PhD days, 10 years ago, something, it wouldn't recognize their voice, and it would recognize perfectly well what all the male researchers in the lab are saying, but for them, it would just not recognize it, and they'd actually have to go in and retrain the voice recognition system for their voice to make it work. And that seems yet another example of the kind of things you're talking about. Yeah,
and we know this is true. We know that we have systems that, it turns out have a difficult time determining whether if you come from, say, Japan, whether your eyes are open or not, because they were trained on people with different set of facial features, or at least groups of people with different facial features. We know that recognition works better on some people than others. And these are not small things. I mean, look, they're not small things anyway, but they're certainly not small things if they're going to be a part of these big, complicated systems that get deployed in the world and have an impact on people's lives. I mean, it's real. But, I think you could make a purely moral argument about this, that it is unethical, that it is wrong not to think about these things. And I completely support those arguments in principle. But I also think that you could make a purely kind of scientific argument about this, or what are interesting problems argument about this, that these are interesting problems. And you haven't solved the problem you claim you solved unless you've at least given some thought to it about how these things would actually work out in the real world. I mean, I think even, the mathematician who proves a theorem about an artificial system that will not turn into something that impacts the world for 30 more years should still be thinking about, the implications of the system that they're exploring and how it might be used. And I think that just should be something that we all do. And it does have these sort of impacts in the real world. I mean, here's a question to ask you, right? Like, what do you think? The people who built the speech recognition systems, why do you think they built systems and deployed systems that aren't well recognized by women? By the way, these are not just recognize women's voices. This is not just, by the way, experimental systems that are out there in the world. I mean, Siri, Alexa, they don't work as well, at least when they were first released. They didn't work as well with women's voices as they did with men's. So how did that happen? And why is that? Is that okay? I mean, is it just a thing that we learned and we moved on, or does it have these kind of impacts? I mean, how do you get there? You build systems, you worry about these things all the time. How do you end up in this kind of trap or with this kind of outcome?
I mean, there's a lot of reasons you could end up with that kind of outcome. I mean, for one, the obvious one is that typically in the room where the systems are built, there would only be males. At least, luckily, it's getting better. But 10, 20 years ago, the vast majority would be male researchers working on this product. And so I think usually you just kind of, it's called dog fooding, right? You build a product and you test it on yourself first before you put it out in the world. Mm-hmm. And so you're dog fooding this on your own team. But if your own team doesn't have the right representation, then that dog fooding is not going to cover it by any means. And so I suspect that's a very big part of it.
And you won't know. So I have this thing I like to say, and I think you've captured it exactly. I like this idea of dog fooding. I tend to express it in terms of invisibility, right? So often when we talk about these kind of issues, when we talk about invisibility, what we mean is someone standing in front of me and I don't see them. They're invisible. And that's a problem. That's a real thing in the world. But I actually think the more insidious problem is a different kind of invisibility, which is you're not in the room and I don't notice your absence. Mm-hmm. So the group of people you're talking about, my guess is it just didn't occur to them that there were no women in the room, and it might matter. It just didn't occur to them at all because there was no women in the room for them to notice there were no women in the room. And I think this is like so many things in life. It's survivor bias, right? It's you're driven by the people you see who get to a certain point, and they end up driving everything else. And it's only much later that you realize that you've missed out on this massive part of the space because you didn't have the right set of people in the room. And it's not that the people you have in the room aren't smart enough or aren't good enough or whatever. It's just that it just doesn't occur to them because they haven't had certain life experiences or because they happen to be much more alike one another than other people who could be in the room. So I think you're exactly right. I think it's dog fooding. You just don't notice that you aren't capturing the entire space. And you're doing just fine. And you just got published. You just got your 50th paper published. Your H-index just crossed 20 or whatever it is you were trying to do. And so all the feedback that you're getting is positive anyway.
Mm-hmm. Now, one of the things I've seen starting to change in this context is to not just evaluate for accuracy, but to have different criteria of evaluation of a machine learning system. It's not how often is it correct, but if I slice the population on which I tested, in each population, does it meet a certain level of performance, right? And that's a very new, maybe it's not a new thing per se. I mean, mathematically, people could have done this all along, but it's a new thing that people are paying attention to it, to get these fairness criteria built into the systems. And it seems like that's in itself sprouting a whole new domain of research on how to optimize for that, both during the training, during the data collection, during the communication out to the world of what are the performance criteria this was tested on. And so I feel like slowly maybe we're starting to move in the direction of capturing some of these things.
Well, and by the way, it builds on stuff you know how to do. I mean, you could argue, we could go back further than this, but I'll say something nice about my advisor, right? So if you go back to Viola and Jones and cascaded learning, right? That's basically what they were doing, right? The unbalanced data set. It's just that we've been thinking about the unbalanced data set in terms of labels, not the outputs, not the unbalanced data set in terms of the inputs. But a lot of that sort of work that was done, the way we think about that problem applies now. These aren't they're interesting technical problems, but they aren't necessarily difficult technical problems, as it were. And I think that's right. So, and this is such a machine learning, statistics, computer science thing to do, right? You just change the objective function and then you get different behavior, and that's what you should be doing. And I think that's right. I do think it's going to have to go deeper than that, right? You are going to have to say things like robustness. Like, is this particular algorithm or is this particular technique going to be robust to various kinds of changes that you don't know? And it could be something as simple as small changes in hyperparameters. Is it fragile? Because if it's fragile, then likely maybe it won't survive when it goes out in different kind of data. I think we should be evaluating not just sort of accuracy or this kind of class agnostic accuracy, but also things like truly out of sample data. What does it mean if this gets completely switched into a different kind of data set that we get used? What happens if it gets used to predict something? You should be asking these questions, I think, and evaluating things. The problem is with this, is that it's got to be the case that it is okay. You can still get published in NeurIPS or ICML or AAAI or any of these places that matter to us, even if you have a negative result. You know what I mean? Even if you can say, look, this really works, but it's fragile in these situations. You can't require that people be effectively perfect before you're willing to give them the okay to be in one of the 20% of people who are going to be accepted for publication issue. There has to be some mechanisms by which you reward the people who are thorough and ask these questions, as opposed to the ones who appear to have the best possible results in a very narrow sense. That is hard. First off, it's hard, but also it's asking a lot of people to completely rethink not only what's good, but to rethink the metrics that they grew up with that validated their own success. because you're in some sense saying, I got to where I am despite the fact that we were measuring everything wrong. You just have to feel okay with that.
And it's very interesting because, I mean, when I think about running machine learning experiments, you work so hard, you get the good result, you get excited, you can finally write your paper. But then effectively, there you come in, Charles. I mean, this should be the whole community, just kind of proverbially speaking, there you come in, Charles, and you're like saying, knocking at the office door and saying, okay, your result is great, but what if I change your hyperparameters around? Does it still work? And if not, I might not be so happy with your result. I want it to be more robust to those settings and so forth. And now all of a sudden you're back to, having to restart in some sense the work on that project in some way. It sets the bar a lot higher very quickly once you start having those expectations.
Yeah, and it's easy for me to say because I've already got tenure. It's amazing how willing you are to change the system once you're already protected by it, right? So I agree. I think this is very difficult, and I think it's the transition itself is going to be pretty hard, but it's coming because here's the thing. Here's the way when I try to talk to people about this. Either we fix it in a way that makes sense, we rethink the way we do these things, or eventually something really terrible is going to happen, and someone's going to fix it for us, and that's going to be much, 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 much worse. So we might as well do it both for our own self-preservation, but as well as the fact that it's interesting and it's the right thing to do. But we're just gonna have to do this, and I think that's fine. I think it's perfectly fine, given everybody's thinking about these problems and they're interesting. It's perfectly fine. I mean, we've done this before, right? I mean, when I was growing up, a million years ago, shortly after they invented fire, I mean, I remember having like the first results of a technique called independent components analysis on large data with supercomputers that took weeks to run. It was like hundreds of thousands of data sets as opposed to gigabytes and terabytes and petabytes. I mean, the stuff that seemed, cutting edge in 1998 is barely even worth having a conversation about in, 2020 or 2021 or Lord knows in 2030. But somehow we managed to accept these changes and what the bare minimum is over the course of a couple of decades. And I just think this is just like that. It's just more what the bare minimum is for us to believe that you've done something interesting. It's changing, changes slowly, but it's changing. And so we might as well take some control of it and try to make certain it's the right thing. And I don't think it's that hard. I think, again, it's easy for me to say, but it's going to happen anyway. So we might as well control that process and come up with something that has at least some scientific integrity to it.
Now, talking about history, Charles, right now you're one of the world-leading machine learning researchers, but you weren't born that way. I mean, maybe somehow talent-wise you were, but I mean, you were not born as one of the leading machine learning researchers. Where in your life do you see the moment where you got intrigued with artificial intelligence and machine learning, and what was the path from there?
People ask me all the time, how did you get interested in AI and machine learning? When did you know? And I think the story is really unfortunately kind of boring. It's I've always known I wanted to do this. When I was 8 years old, I knew I wanted to do computer science. I knew that I wanted to be a professor. I didn't know any of these things meant, mind you, but I knew that I wanted them. By the time I was in high school, I knew that it was going to be AI. I'd seen robots. I wanted to build, data from the next generation. I knew by the time that I was, before I went to college, that this is what I wanted to do. I'd been playing around with a friend of mine who liked to build robots from remote control cars. And I just knew this is what I always wanted. And in fact, I only applied to one place for undergrad because I knew that's where I wanted to go. I only applied to 3 places for grad school because people told me I should apply to more than one place. But I knew where I wanted to go, and I knew what I wanted to do. Now, I don't recommend this for anyone that was dumb. I just didn't know any better, and there was no one around to tell me that what I was doing was crazy. But it's just sort of what I've always wanted. I've been thinking about and writing about AI and what that meant to me at the time from, the time I was a teenager. I just always sort of wanted to do that. And once I got to grad school, and I met people who were actually doing research in the space, and I began to understand what it really meant both to do research writ large and also what it meant to do AI and machine learning. I knew that I had lucked into the right answer, and this is what I was going to be doing for the rest of my life, at least the rest of my research life. And it's been great. I have zero regrets for any of those decisions that I made, because this is just fun. But I can be a small part of building a system that one day people think of as intelligent, and intelligent in the way human beings are intelligent. It will have all been worthwhile.
I think that's so fascinating. As an 8-year-old, you already kind of had this vision for yourself to be in computer science, and from there evolve to AI. Myself, as an 8-year-old, I'm not sure I even knew what a computer was at the time, and that it was possible to program it and to do something interesting with it. It was more like running after all kinds of different balls for playing different sports was on my mind. Very, very, very different starting.
Well, I was reading a lot of books.
Right. So it might have been the books, might have been part of the inspiration. Is there any book that stood out to you till today that might have been one of the key triggers?
Oh, wow. That's a really interesting question. So I was really into science fiction. And at that point in my life, I was reading so much Robert Heinlein. I was reading like 10 books a week. I was really, really, really into this stuff by the time I was, certainly in my 10, 11 years old. And I was reading lots and lots of comic books, and I really liked all of the science fiction ones. There was these special comics that would come out that were about science fiction, and I was really, really into those. I don't know if the particular book stood out. I mean, I remember books that I've kind of carried with me over the years, but when I think about them, none of them really had anything to do with AI. But they had, a lot of them had to do with aliens, or being in an alien culture and being different from everyone else, and trying to figure out how people were the same. Stranger in a Strange Land, even Spaceman Jones, which is a book probably almost nobody, unless they're really into Robert Heinlein, would even remember. There wasn't a particular book that drove me down there. It was just all a piece of the fantastical and living in the future. One of my favorite comic books growing up was Legion of Superheroes, which took place in the 30th century. And there were all these amazing things and robots and various things that were running around. Now it's the 31st century, so it's always 1,000 years in the future. And I really wanted to live in that future because it just seemed great.
That's so fascinating. Now, you said you applied to one school, went there for undergrad, and you knew where you want to go for a PhD. Where did you actually go?
MIT, the Georgia Tech of the North, which is where I went to undergrad. So I applied to Georgia Tech for undergrad and no place else. And then I graduated to MIT and 2 other places. I applied to MIT and 2 other places for grad school. And I remember visiting MIT. What I remember about I remember 2 things about visiting there. One is that it was really, really cold. And Boston is a very cold place where it gets dark very early. I remember that. And I remember this feeling that no matter what I was interested in doing, somebody in that building, Tech Square back then, someone in that building would know how to do it. And that it was just this kind of world of really smart people trying to solve problems. And I just thought, this is great. I've got to come, despite the cold. And I went, and I was there for many more years than I cared to talk about. But by the way, while I was at MIT, while I was in grad school, something really important happened, which I think kind of matters for understanding the specific set of problems that I care about. So I was in the AI lab, which is now merged with another lab called CSAIL at MIT. And I spent most of the year there, but I spent about 4 months out of every summer and 1 month out of every winter. So about 5 months out of the year at Bell Labs, New Jersey, which was also another cold place. And the work that I did at MIT and the work that I did at Bell Labs and later AT&T Labs were very different from one another. The people at Bell Labs and AT&T Labs when I was first there were what we would call good old-fashioned AI people, knowledge representation and a lot of symbol pushing around, and they cared about building big systems that were going to work. And at MIT, it was, here's the equation, and it was machine learning and statistics-based stuff. And they were very different. They were almost ideologically different places. But I kind of grew up in both of those kind of research traditions. And so when people would ask me what I did, I said, well, I'm a machine learning person, but really I'm an AI person. I'm really interested in is solving the problem of building artificially intelligent systems. And it's the systems part really matters. The the way to do it, I thought, and I think, is through this kind of data-based, statistics-based kind of view of the world. In part because I thought the learning really mattered more than almost any. How can you be intelligent if you aren't learning and adapting? But having been sort of raised by two different sets of parents who had kind of different ideological views of what was the right way to do AI research was I think very important to shaping the kind of work that I ended up doing when I finally graduated.
Mm-hmm. Then after graduation, what did you do?
So after I graduated, I spent 4 years at that point, it had become AT&T Labs, and worked on, that's where I started doing work on AI agents, machine learning agents that actually had to interact with people and had to interact with people in social situations. Probably the work that I did that I'm most proud of from that time period is something called Cobot, which was a social statistics agent, and started really thinking about reinforcement learning and all of these techniques. How would they really work if you had to deal with messy problems? And there's nothing messier than people. So we would build these things. And I think one of the reasons I think about all these problems, machine learning as being systems problems, is you can't build a system like that that's going to be talking to, thousands of random people from all over the world who don't have a particular thing that they're doing, unless you can build a robust system. So we built this thing that would build models of human beings and kind of predict their behavior and what they might do next and how you might do something in that world. But it turns out you couldn't just build that system because people wanted to talk to it. So now we had to solve all of natural language processing and natural language understanding, and we had like a week to do it before we got in some kind of trouble. And so you end up making up some way of just making that work. It was very hacky, but it was very cool. This is actually Michael Kearns' idea, the specific way that we did it. And, I found myself building these big languages and these big systems in order to kind of make it work and to think really hard about the particular domain that I was in order to do something really cool. And if I hadn't done that, I could have maybe published a paper about, prediction accuracy of what someone would do or say next or what action they would do, but it wouldn't have solved the problem, because the problem was building something that people would want to interact with in their kind of everyday social lives. And so I spent many years working on that. And then 4 years later, during the unfortunateness of what happened with AT&T, the labs kind of collapsed for a bunch of reasons, and people kind of went off to the four winds. I became a professor, went back to Georgia Tech where I did my undergrad, joined the faculty there as a young assistant professor, and I, went through the process and eventually ended up where I am. One thing that's different about my journey in academia from most people is I came in as an assistant professor. The day I became an associate professor with tenure was the day that I became an associate dean. So during my time as an assistant professor, which is crazy, by the way, nobody should do that. But while I was an assistant professor, we were building, we completely rethought our undergraduate curriculum. And I was the committee lead on this new way of thinking about undergrad education, ultimately called Threads. And because of that, I started getting really interested in curricular reform. And so I became the associate dean of undergraduate education the same day I became an associate professor. 3 years later, I went up for full. And the day I became a professor, I also became senior associate dean. And I found myself spending as much time thinking about education and organizations and how you support and deliver both research and education as I did thinking about reinforcement learning and game theory and all the things that I was doing on the research side. And so these things kind of went in parallel until I eventually, admitted that I was an administrator as well as a researcher. So my journey was a little different in that way, but I kind of feel like it sort of matches, it makes sense to me. It makes sense to me that if you really believe these kinds of things about how research has to touch the world and you have to think about them as systems, eventually you find yourself thinking about the way education works and higher education works. And, once you realize you got to have the right people in the room, then you have some responsibility for thinking about how you're going to actually bring access to people so the right people can be in the room. And, then next thing you know, you're dean. This is just kind of how it goes. And so I think those are kind of the right things for me personally anyway. And I think to me, they're the same thing. caring about AI and machine learning and what that means, and caring about higher education and building systems and supporting researchers and new students. They're the same. It's the same problem. It's the same thing.
We are dropping new interviews every week, so subscribe to The Robot Brains on whichever platform you listen to your podcasts. Now, Charles, I've of course been reading up on a lot of things you've been doing, and one of the things that really stood out to me that I think you probably started doing as a dean, pushing that forward, this notion that many schools will essentially advertise how small a percentage of the applicants they are going to be educating. Like, we're only going to educate 3% of the applicants that want to be educated here. Look at how elite we are, right? And you've been starting to flip that around. Can you say a little bit more about that? And when did you start thinking about this?
This idea of good means you say no. Goes way back. It's built in the way rankings work. It's sort of built into everything. And it's sort of how we evaluate. By the way, my own research from way back when about modeling people and getting people to do things, turns out one of the most powerful things you can do to get someone to do something is to convince them that something's going to go away, that something is scarce. Scarcity is a huge motivator. This is why Black Friday works, right? This is, you got to buy this now because the sale will be over and you'll never be able to buy it again. This seems to be just something about human nature, that if something's going to go away, if something is rare, it's important, which is why we pretend that diamonds are rare, right? I mean, it's built in. So it's not surprising that our higher education system is set up this way. And we know it's a better school because fewer people get in. We know it's a better school because more people want to get in. That's a positive feedback loop, by the way. And that's kind of where we go. And it's weird, right? It's weird. It engenders all of this very strange behavior, both by the people who are teaching and by the people who are being taught, right? You feel like I got to get into this one school or it's not going to work. Here's an interesting statistic for you. 2 years ago, Georgia Tech became only the third public university in history to have an acceptance rate below 20%. The other two being Berkeley and UCLA. Lots of private schools have this. But when you talk about large schools, very few. It's actually not as hard to get into colleges as you think it is. It's hard to get into the specific college that you think. But we have this in our heads, right? That every school you want to go to, it's like, it's impossible to get into. It's a lottery, and then that generates panic. And now I have to spend all this money to make certain I got to apply to all these places. It's just a mess, right? Everything about this it's a mess. It doesn't make any sense. If our goal is to educate people, then we should be judged not by the people we say no to, but how the people who come to us end up at the end. The previous dean of computing, Zviga Lil, used to tell this joke that I really liked, and it boils down to the way you can tell a good school from a bad school is that in a good school, the output isn't much worse than the input. Right. So good universities do minimal damage to their students. But what that really means is, you're a good university because all your students are good. So what behavior does that drive? That drives being hyper conservative. It drives, you talk about, maximizing accuracy, and that's a problem for machine learning. Well, guess what? That's how higher education works. All you care about is having no false positives. This is true for faculty hiring. This is true for promotion. It's true for grad students. It's true for admitting undergrads. You don't want to admit someone who's going to fail. And who cares if you say no to people who would succeed, as long as you don't say yes to people who won't? Because those people don't, there's a million people. Well, there are 20 times more people who want to be at your university than there are slots for them. So that's fine if you say no to people you shouldn't say no to, so long as you don't say yes to people you shouldn't say yes to. So that drives all kinds of really, really, really bad behavior. So when MOOCs happened, when we suddenly had this kind of idea and everyone was saying, it's going to change higher education, it's going to disrupt higher education. Nothing ever actually disrupts higher education, but it's going to disrupt higher education and everything's going to be free. I never really believed that. But one thing that I think we believed was that we should be able to educate more people and it should cost less because the sort of incremental cost to us was small. So we started the Online Master of Science, Computer Science. And the goal was to be exactly, if not better, exactly as good, if not better, than the master's program we have on campus, right? It's a top 10 program. We want to have a top 10 online education. We want to just open this up to the world. And we wanted, by the end of the first year, to basically say yes to every single person we believe who could succeed. And if you do that, then you'd be able to say, we know we're good because we take everyone who might be able to succeed and we give them the tools they need to be better. And so we did that. But just because we have this program doesn't mean that people who would be able to succeed are going to be able to do anything with it. So it was important to make it affordable. So accessibility isn't just about affordability, but it does need affordability. So to get this degree program cost about $7,000 total, the entire degree, as opposed to the $46,000 it cost you to come on campus. And we opened that up and it really worked. We now have, so it's been 6 years, we now have 11,000 students in this program. We are graduating somewhere between 1,000 and 2,000 students a year in this. At this rate, just to give you a sense of scale, if you take there are more students in this program than every single graduate student, master's or PhD, in all of sciences and all of engineering at MIT combined. Right?
Wow. We
are, if this stays steady, which it might not, but if it does, then something like between 1 out of 8 or 1 out of 6, every master's student in computer science in the United States will be a Georgia Tech grad. And what's really interesting about this is almost none of these people would have pursued a master's degree. They couldn't. They were working full time. They had mortgages. They had all of these kind of things. But they're able to do this. And most of them get through. And a lot of the people who don't get through, they leave with 4.0s. It turns out they didn't want to go through the trouble of getting a full master's degree. But it's been amazing. And here's another thing about it. I'll tell you a couple of things that are really amazing about it, aside from the fact that it worked, is that it turns out that we see students in this program who are not only doing well, they are statistically indistinguishable from the students we actually admit on campus, right? So it's not that we've opened this up and then, some people come in and they kind of get out. They do just as well as the students who are on campus, right? There's 7 times as many of them, at least, and actually much more than 7 times as many of them, but 7 times as many of them apply at any given time. And we're admitting all of them, or at least all the ones we think who can succeed. And they're doing just as well as the 9 or 10% we admit, and less than that we admit into our graduate program on campus, which suggests that there are many more people out there that we really had cranked up the sort of false positive, false negative trail. The second thing I'll point out about this is not only do they succeed in general, but they look very different from the students we admit on campus. I think one professor said something that I think is really true. Even as a dean, I still teach in this program, so I teach something like 3,000 students a year in this program. In any given year, I will teach more women in computer science than I will have taught in all of the time up to that point on campus. Wow. At any given year, I will teach more Hispanic students. I will teach more Black students than I would have the entire time I was a professor up until we started this program. So you're having a real impact on not just more people, but more kinds of people you would have otherwise, people from different backgrounds. And it's making a difference, at least if you listen to them, it's making a difference in their lives. And I'm very proud of that. And I think it's proof that we're doing it wrong, that tying in our tying in how good we are with how often we say no is not only ethically suspect, it is kind of on the merits wrong. It's just wrong on the merits, just on the merits. People could do better. We could bring in more people. They will do just fine.
Do you think, Charles, there's something in the way you set up the program that you are attracting a more diverse pool of applicants as a consequence, or is it just the way you do the admissions process?
It's both. It's both. The admissions process matters, right? If you're accepting instead of 8 or 9% of people, you're accepting at this point, you're accepting almost 80% of the applicants. By the way, we didn't talk about this, and it's a much longer story, but I will point out that once you say you're going to accept everyone you believe you can succeed, which implies you're not accepting people you don't believe you can succeed, then you suddenly have to address the fact that we actually have no idea what it means to succeed or to be able to predict that someone's going to succeed. If you're at Stanford just to pick a random university with an acceptance rate in the single digits. The average incoming GPA is probably a 4.0 if you don't adjust it for AP courses. I know that's true for Georgia Tech. The average SAT score is going to be north of 14 or 1500. And it'll be different for different majors, but generally speaking, it's going to be high. Who cares? All of the people you could randomly choose among the top half, and every single one of them will succeed, right? Or have as much a chance of succeeding as anyone else. And so even though you say you have standards, you actually have no idea you really don't know how to predict whether someone will not do well, because you never even have to address that question. You never have to look at the people who are on the margins by whatever measurement that you're using. You just know that all the people who are applying to you, the vast majority of them are above bar, whatever that bar is, and they'll be just fine. And so you shape the class the way you want to shape the class. So I think that admission process is very important. But I also think that, the fact that it's going to cost me $300 a semester instead of $13,000 a semester matters a lot. That I can do it without moving halfway across the country matters a lot. It feels like an opportunity to people who otherwise feel like they wouldn't have an opportunity. So the fact that it exists and that it is attractive in and of itself because it is low barrier to entry and low consequences to potential failure attracts more people. And by dint of that, will attract people from different backgrounds. Large percentage of our students, are coming from non-STEM backgrounds who want to switch into a CS or a computing background. And dipping your toe in for $300 is a whole lot easier than dipping your toe in and changing your life for, $20, $30, $40,000, $50,000. I think that's a part of it. And then the admissions is the rest, because you don't even have to ask these questions. You just don't have to worry about it. You look like you can do well. We're going to give you an opportunity.
When you say, Charles, dipping your toe in for, was it $300 as well as that?
So it's, so I guess it's more than that now. I'm thinking about what it was when it first came in. So it's the tuition itself is going to be $500 or so, and you got to pay fees. We could work this out. You could just take $6,600 and divide it by 6 or something. Yeah. So it's divided by 9. So yeah, it's somewhere around there, $500-$700, some of which is refundable. So if you start this and you're like, I can't, this is too much for me, you can actually get most of your money back in a particular semester. So you really are only putting $500 up in any given semester anyway. So the potential cost is low. At least it feels low. It's actually not low. It's an enormous amount of time, but in terms of money, it's something that you can kind of afford to do, given that the upside is so big. And I think that matters a lot for this.
I love it, Charles. And what I also really like about it is, I think when I look at the students at Berkeley and I see, okay, what are they most intrigued by that maybe the natural setup doesn't give them? It's they're not being taught by people from industry ever, right? Or very rarely. It's not never, but it's rare. They get taught from people who are in academia, who often spend a bit of time in industry and so forth, but their TAs, the TAs are students who are a year ahead of them or 2 years ahead of them. And that's great because they've had a similar experience, but it doesn't bring in the perspective of somebody who's been working in industry for 10 years and can contextualize, what's being learned, what they're learning in this class to, on the job at whatever, this or that company I was at, we actually use this, or we kind of use it, but in this different way, and really give that real world additional perspective.
Yeah, I will tell you sort of our students, the median age is somewhere deep in the 30s as opposed to early in the 20s. But also, a lot of them have advanced degrees in other areas. A lot of them are VPs or, developers high up the food chain at the companies where they are. They've been to multiple companies, and they bring all of this to what we do. I know at least in the early days, we had a kind of data-driven health systems class as a part of as an offering. And, apparently there were real MDs in there because they wanted to understand this stuff, and they're coming in as doctors. So imagine being in a class like that where you're learning about how to develop health systems, and you're worrying about building, digital medical records and all these other things. And there are real doctors in the class with you. They don't know they can barely code Python, but they're doctors, and you can code and, write a system over the weekend, learn a new programming language if you want to, but, you've never cut open a human being. They have. I mean, imagine being in that kind of environment. And this kind of thing really lets you do that. I just think it's amazing. It's to me, it's opened my eyes to the possibilities of bringing in lots of people at various stages in their lives and having them be a part of this kind of never-ending process. And if I can be just a little trite for a moment, isn't that the whole point of a university, right? To create a learning environment that you get to be a part of and that everyone benefits from. I mean, the reason you go to Berkeley, the reason you go to Georgia Tech, as opposed to some other place, there's two reasons. One, because you're going to get a better job, which is just a fact about life. But the other is you're going to be exposed to the best students, the best faculty who've had all of these experiences, and you'll be able to kind of swim in that, and you'll come out of it in a more interesting place as a result. But then you're a more interesting person. You've been out in the world for 20 years. Why aren't you back in the swimming pool, as it were, and bringing all that knowledge and that experience together? And just imagine what would happen if universities really worked that way, that you really had all these people from the 1930s to the 2030s all in a room together all the time. I mean, that'd just be great.
I love that vision. And the one place where I kind of see that vision already play out a little bit for a long time, of course, is business schools, right? Business schools bring people back in who've been in industry, and they learn so much from each other's experiences. It's just that somehow we haven't been doing it in other disciplines.
Right. And in fact, it makes a lot of sense too, because insofar as business is a science, it's definitely an empirical one, right? And the experience really matters. So now imagine it's not just your business school, because of course the way business schools work, as I have been told many, many times by colleagues in business schools, is cohort model, relatively small, tight knit. It's great. Mm-hmm. We want that to scale. I mean, if we do nothing well, it's scale, right? How do you take that and make it work? The trade-offs. So how do you take that and make it work with 11,000 people at a time, 40,000 people at a time? How do you scale up those experiences and let people kind of build things as they go along? I will tell you, I don't have a lot of data to support this, but I think it appears to be true. The students who do well in these kinds of environments are the ones who find a community, who find a group of people with whom they can feel comfortable, who are going through what they're going through or have gone through what they've gone through. And it looks to me like those people do well and they succeed. And so a lot of our work is actually around supporting the communities that the students create over time. In fact, when people ask me questions about, well, how do you make something like an online program like this high quality work? I tell them the first thing you have to recognize is that it's not translating the class, which is work. It's real hard work. Just like making a podcast is hard work. So much more goes into it than the final product you see. It's actually all the other things that have nothing to do with the specific course. It's the advising of students who are asking questions, not about, can I get 2 more points on this assignment that's worth 7% of my grade? It's, well, should I take these 3 courses in sequence? Do these things work well together? It's the question of the trajectory through the learning experience. It's the advising, it's the community experience, it's the networking, the building of cohorts and friendships. Those are the parts you have to support. Getting the class videotaped, even in very clever ways, and getting the information out there and making certain that it's hard to cheat on tests and all that kind of stuff. Those aren't anywhere near as hard as creating the sort of learning environment itself and making it so that people can get what they need in order to succeed in that. That's where you have to put all your time and energy.
Now, of course, you actually wrote a book about this called The Distributed Classroom, right?
Yes.
Came out somewhat recently.
Well, it's coming out officially in September, I think.
Oh, it's not officially coming out in September, The Distributed Classroom.
Mm-hmm.
Is that what that book is going to focus on a lot, help other people to succeed with building these communities?
So it's more broad. It's broader than that, right? By the way, it's with my co-author David Joyner, who is fantastic. He cares very much about education as a kind of research question as well as a life question. I love having conversations with him. He's actually over all of our online stuff in the College of Computing. The point of this is to kind of explain what the ideal university classroom learning experience would have to look like. And I like to think it raises as many questions as it does answers. But yes, that's what this is. That's what this is about. Less about the, how do you create a MOOC that does this, or how do you create a program that does this, but more the kind of larger questions around what does it mean to actually create a learning environment in a world where things can be truly distributed? What is it you need to think about? What are the things that aren't obvious until you've lived through it? Those are the kinds of things that we're talking about. And these are the things that I think we'll be continuing to talk about when we write the next book and the book after that. We get to talk about this and we do those kind of things. I think those are very hard. For me, and like I said, I at this point, I care about the university. Like, what does it mean to create these big learning environments when they're going to be distributed across time, space, and experience? And I just think that's where all the interesting things are going to go. It's not going to be these schools go away because you can just take the MOOC from, your favorite machine learning or robotics person over here in this elite university that otherwise only accepts 4% of its applicants. The future, the universities that go away will go away because they won't be able to tell a story about why you want to physically be where they are, and what it is that they bring to the table in terms of learning and experience that you're not going to get somewhere else. So I think most of us are going to figure out what our own special sauce is and be able to advertise that experience separate from the specific coursework or the specific tests that will make people want to be there.
Now, Charles, with the drastically increased diversity in the online master's program you have at Georgia Tech, do you think that starts making a dent into kind of diversifying our computer science engineering workforce? Or how optimistic are you about that?
I'm optimistic, and I'm optimistic by nature, but I think that there's two things to point out. One is the diversity is higher in terms of absolute numbers, not always in terms of percentages. But the problem is such that we need so many people that diversity will perforce come out of it. And so I'm very happy about that. But it is interesting, right? You do learn some interesting things. So, for example, the diversity for our online program versus our on-campus program for underrepresented minorities, particularly Black students, but underrepresented minorities is much higher than it is on campus. But when you look at women, you actually get a different story. So I haven't looked at the data in a little while, but last time I dove into this, which was a couple of years ago, and I don't have any reason to believe that it's changed, what you see is the percentages were actually worse. And in fact, we drew some criticism for this internally when we tried to figure it out. So I stared at the data for a long time, and I noticed something that kind of, at least to me, explains it, which I think speaks to a larger issue. Instead of comparing women to women, women online, women on campus, and saying, what are the percentages? If you instead compared women who are citizens of the United States to women who are citizens of the United States and women who are foreign nationals versus women who are foreign nationals, the percentages are the same. The difference is that, at least when we started, 85% of our on-campus students were foreign nationals. Only 15% of our online students were foreign nationals. That number is now closer to 30, but whatever, it's still highly skewed. So the reason the percentages were lower is because it turns out if I were to randomly choose a woman pursuing a Master's of Science in Computer Science at Georgia Tech, the probability that person was not born in the United States is very high, right? Mm-hmm. So the shift into online was not just more people, it was a shift from 85% outside the United States to 85% inside the United States, right? Mm-hmm. And which means that our problem, or at least one interpretation, is that our problem of increasing the number of women in computer science, at least in grad programs, is an American problem. And there's something going on in the United States that is driving this disparity, and that disparity is lower outside the United States, or at least it's lower for people from outside the United States who come to the United States to study. And I won't pretend to know enough to understand why that is, but it's pretty clear from the data that that's kind of what's going on. And you can see it even in this case, where if you, at least you split it out and you condition on the right variable, as is often the case in these kind of data analysis problems. So in terms of percentages, we need to do better. In terms of absolute numbers, it is just an unalloyed win. Mm-hmm. Just more people. You never would have seen these people who are now in the conversation and able to impact the field. So I'm very happy about it, very optimistic that will help us, and that in the long term, you will see that change have an impact on how business is conducted in universities and how we evaluate people and how we bring new people in. And that will, you'll have another virtuous cycle.
That's so interesting. Now, I got to say, initially, when I was thinking about the numbers you're putting out there, 85% in the program is from outside the United States. That's, of course, you're specific to the master's program, right? That's the master's program in computer science.
That's right.
Got it.
Exactly right. Master's of Science in Computer Science, which is hardly unique to Georgia Tech. I mean, Tech has a pretty large MSCS program. A lot of universities do not, particularly ones that don't come out of an engineering tradition, where computer science doesn't come out of an engineering tradition, but comes out of, say, a math or science tradition. But you see a lot of, you see for a lot of programs, you see the kind of skew from domestic versus non-domestic students. By the way, that's not a value judgment. It's just an observation that might explain data that you see downstream of why did you see certain kinds of people and what things they happen to be interested in. In fact, if you look at people coming into our PhD program, this is very old data, but if you look at people coming into our PhD program and the fields they're interested in studying, say 5 or 10 years ago, huge split depending upon whether you're coming from out of the country or inside the United States.
Awesome.
Yeah, I mean, and I think they're probably easily explained. I mean, it's probably easy to explain this if you know enough about how different programs are sort of taught and developed over various parts of the world. But it does have these kind of interesting impacts on the students you see and where it is they're trying to go and how they look different from one another. It's
really important to also educate our government officials, regulators, and so forth. And that's something that is not easy, yet very important to get right. And this is the government, both within the military, outside the military, and so forth. Now, you have actually testified in Congress. In 2018, you testified in Congress. I'm really curious about that. Like, how does that even come about? How did they decide to invite you and other AI researchers to come to Congress? And as you think about that, what's the message you really want to get across when you, let's say you get to go to Congress again, what would you really want to get across to the government? So testifying in front of Congress is, I've done it twice, once on education and once on AI. They were very different experiences, let me tell you. But if the question is, how does this go about? Well, your university, wherever you are, I promise you, your university has people who spend a lot of time thinking about the government, and they have connections. And when someone from an office says, we're going to do a panel on this and we're looking for experts, they're saying, hey, we have various people. So you have to be known. If you're interested in having these conversations, you have to be known to the people who are communicating with, in this case, the federal government, which really means the staffers for the various congressional, the folks in Congress, and say, we're interested in that and this, and we're a place that is interested in having these conversations with people. And then it's one of these things that once you're known, you tend to kind of keep getting asked to do various things. It's really quite an interesting thing. So for the AI panel, I was actually the only academic on there, I think, but for the AI panel, it was very interesting because the people who were on the subcommittee, who were to whom we were testifying, were genuinely interested in understanding AI and how it might impact the government. So I think we were first in like a 3-part series, what can we do? And it was clear that everyone there had an agenda. I mean, among the Congress folk had an agenda of specific things that they wanted to kind of get across, but they were mostly there to hear from us, and they were asking us genuine questions. So I think your goal in that situation is to understand the 1 or 2 key things, given the question, given the specific question in front of you, the 1 or 2 key things you want to get across, and to make certain to get those things across, and to always tell the truth and what you really believe. And to remember that the answer that you're giving is not just to the specific question being asked right now, but this will be referred to and thought about 5 years later, 10 years later, maybe even, depending upon what it is. And so you're not
remember, you aren't talking to the person in front of you asking the question. You're talking to the nation. You're talking to a broad set of people who are going to take this information and do something with it. Just like being a professor, you're talking to a large group of people. That is your audience. Your audience is broad, and you have to make certain that that audience is hearing what you're saying so that they can make whatever decisions they want to make. What I wanted to say then, and what I want to, and I think what I want to say in the future, is that AI is important. It requires serious thought about how it's going to get used in order for it to be deployed in a way that is useful, and that if you are not unfair and not negatively, doesn't have negative impacts on people, and that you have to think about it as a whole system in order to do that. And insofar as the people asking you the questions genuinely want to know the answer to that, it's all to the better. But even if they're not interested in it, they have their own agenda, they have a particular outcome they want. The congressional record is the congressional record. So you're speaking not just to them, you're speaking to everyone else, and keep that in mind. I would be more than happy to testify again about any of these issues, whether they're purely on the education side or they're on the AI research side, because I think it's important. And it's important that the people who are passing our laws understand what the issues are. And by and large, they are trying to do the right thing around these kinds of technological issues. And they are aware that they do not understand the nuances of them. And you, when you go and testify, should be aware that you do not understand the nuances of all the ways that the regulatory state works and how things have to be kind of pushed into those little square pegs have to be pushed into round holes. And so you go in with a little bit of humility, but knowing that you know something they don't know and that they're interested in hearing it, and it all kind of works out. So that's my take on it. I really enjoyed it. I will end this on this. I think that we do ourselves a disservice as researchers if we do not realize that it is important for us to have those conversations. It's at least as important as that best paper award that you got 3 years ago for whatever it is that you did. This is a larger audience and will have a huge impact. And you need to be careful about your words and what you're trying to say. I think it's one of the most important things we can do.
I couldn't agree more. I mean, the government has so much influence on everything that happens. And for the United States, the government has a lot of influence all across the world in what happens. Mm-hmm. Maybe when you look back, your testimony on AI was about 3 years ago, right? Do you already see some? Do you see some effects of it in various places?
My testimony? I don't know. I mean, you'd have to ask somebody else. But I will say that the world has certainly changed in those last 3 years. We're certainly more aware as a community, but also as people outside the community are much more aware of what AI can and cannot do. Well, certainly aware of what it can do and the impact that it can have. I think it's going to accelerate. I think people will spend a lot more time thinking through how the deployment of the kind of technology we're creating can actually be used to do interesting things in their domains, which is going to increase pressure on us to do more and more of that. I think as educators in particular, we're going to have to come to grips with the fact that we are out educating people who are not interested in doing what we do, but are interested in using what we do to do the things that they're interested in doing. And that we have to figure out how to get that information to them, meeting them where they are, so that they can do really interesting things. Because basically we're going to be handing a lot of people machine guns, and they need to be trained on how to use them. And if we just go, oh no, you've got to do it the way I want to do it because I'm a computer scientist and I know what I'm doing, and I don't really care about your problem, then we're all going to be worse off for it. We're not too long away from a time when you can't get a degree, you can't get a bachelor's of arts in history without having taken 2 or 3 computer science or data science courses. We're pretty close to that now. So that means our audience is no longer people who are going to just build robots with us and, late at night in our parents' basements. Instead, we're talking to people who are going to try to understand how to use the tools we're developing to make decisions that will impact people. And that's an awesome responsibility.
Wow, that's some great advice, and I think a really nice way to end our conversation, Charles. Thank you so much.
Of course. I enjoyed every bit of it. I so enjoy talking.